Thank you for inviting me to speak. My talk's going to be about some stuff to do with operads, some stuff to do with functor calculus, and then even some very basic equivariant homotopy theory. And so not everyone has the same background, so I encourage you to ask a question if I've kind of assumed some definition that you don't know. But there is one thing that everyone knows, everyone agrees on, and it's to be skeptical of the word geometry. So let's begin. So here I've given us a picture of something you would study in geometry. It's a manifold with a tangent plane at a specified point. And so the idea of Goodwillie calculus is to say that sphere is a category, and that tangent plane is what's called the stabilization of the category. It's written SP of C because that's what it means, like spectra in C. Okay. There's a very kind of beautiful formalization of this idea. It goes by the name tangent infinity categories, and that is not what I will be doing. Quickly, we got to introduce an introduction to the kind of linear part of Goodwillie calculus today. And so I have to tell you what I do Goodwillie calculus to. There's something called a differentiable category, differentiable infinity category, and this just means there's a Goodwillie tower. There's a Taylor tower of approximations, and it behaves in a reasonable way. Okay, now what is not always assumed is that I'm going to actually assume that my category C has that its stabilization is equivalent to some localization of spectra at a homology theory E. Now, this is not so important that I use the word spectra here. Instead, you could think of this as maybe chain complexes, and then somehow this E is basically changing the field, right? Maybe I'm using, instead of like integral chain complexes, I'm using a localization, which is rational chain complexes. Okay, but I have some theory of Goodwillie calculus that applies in either scenario. So, associated to a functor, which I'm always going to assume is from C to its stabilization, is a tower. Okay, we saw the very beginning of this tower here. P0 of f is the value of f at the 0 point of the category, and P1 of f is the excisive approximation. Okay, P2 of f is going to be some quadratic approximation, and so on and so forth. And maybe the most important thing is that when I compute the homotopy fibers, at every stage is in some sense computable. It always looks of the form a derivative spectrum smashed with the stabilization functors to the n, and then I take homotopy orbits of that. So this derivative functor is just some symmetric group acting on a spectrum, and this is just a functor that I can always write down. And then the statement of Goodwillie is that somehow, if I just look at things which appear are concentrated in degree n, the derivative spectrum completely classifies it when you care about its symmetric group action. So the fibers of the tower are extremely well understood. Okay, so what notion of geometry are we going to use? Well, the category of polynomial functors is something I can consider. A polynomial functor is something for which its Goodwillie tower converges at a finite stage. This is a perfectly good category to consider, and if I just take what algebraic geometers tell me should be true, is that the notion of polynomial functors or polynomial functions tells me the definition of geometry. Okay, so a polynomial equivalence between categories C and D is going to be an equivalence of their categories of polynomial functors. Okay, now it's very important that I've assumed my localization, or that I've assumed my stabilization is spectra or some E local spectra, because it gives me a notion of the pointwise smash product. Okay, if I don't have a pointwise smash product, it doesn't make sense to ask for a symmetric monoidal equivalence. Okay, so this is something I can do. Is it ever interesting? Okay, here's somewhat of an interesting example, is that if I take the category of pointed topological spaces, it has its polynomial functors, and they actually agree with the polynomial functors where if I just took n connected spaces. Okay, so even though the objects aren't the same, the categories aren't even equivalent, they are polynomially equivalent, okay? So the notion of geometry we're using is something which is, capturing the Goodwillie, polynomial function, okay? Something we can study. So let's just test this out in a very simple case, okay? So, right, we said there's this tangent infinity category of C, which is just the stabilization of C, okay? It's gonna turn out that this is something that we can recover even if I only know the category of polynomial functors with its symmetric monoidal structure. Okay, so the idea is to just figure out what it means to be linear in a way that only uses categorical and monoidal information. Okay, so I mean, when I was figuring this out, I said, let's think about polynomial rings and what captures kind of the things which look like a constant plus a constant times x. Okay, it's just I want to capture something as like the linear things are somehow indecomposable. And so I just say something about extensions by things of this form. And I say, okay, let me look at what this is. This is a homogeneous functor. There's three things going on. Okay, I have some kind of thing which is like the derivative spectrum, or there's some coefficient x, and then I have this orbits, and then I have this g to the n. Okay, tensoring or smashing by x is actually a categorical construction you can prove. Any stable category has this kind of tensoring formula, and so it turns out that the smashing is actually kind of preserved by equivalences. Homotopic orbits can be written as a colimit, and so it's preserved by equivalences. And then the important thing is that g to the n is preserved because we've assumed our equivalences are symmetric monoidal. Anyways, here's some basic characterization of a linear functor, and it's preserved under equivalences. And so therefore, we can recover the linear or the things with only 0 and 1 terms from just an abstract polynomial equivalence. And there we can get the things, right? What was called linear before in the first or the second talk was when f of 0 was a point. And this is what I call the one homogeneous functors, okay? So the one homogeneous functors by Goodwillie are exactly classified by their first derivative, which is just a spectrum. And so if I look at the one homogeneous functors, this is preserved under symmetric monoidal equivalence. And so this recovers the stabilization of C. Okay, that, I don't know, sounded like a lot of words. It's actually a very simple result. Okay, so the geometry captures the infinitesimal neighborhood of a point. And that's what you would expect. Okay, so I'm just extremely glad that Marcy talked about right modules and I wasn't the first one that had to. Okay, so I have some notion of symmetric sequences of objects in E-local spectra. And this has some type of product in it, okay? Now it's always fun when you go to a talk on Operads because there's always a new and possibly incorrect formula for the composition product. And here's mine, okay? It actually has a very nice combinatorial description in terms of trees, but I assume that most people have seen something about Operads, but it exists, okay? So if I have a monoid for this associative product, then this is what an operad is. And given an operad, the reason I've described it in this way is because if I have a monoid in a category C, I can just define what a right module over a monoid is, okay? I have maps, just M tensor R to M, right? And this, if this is suitably associative and compatible with the multiplication, then this is what it means to be a right module, okay? So in particular, a right module is a symmetric sequence with the right action. Now, what does this have to do with Goodwillie calculus? Now, when I have a functor from C to stabilization, I always have this very uninteresting right module structure of F by the identity, which is just equality, okay? So I have this right action, but it turns out that this right action is very interesting once I look at the derivatives of this action. Okay, recall these derivatives are the things that classify the homogeneous layers. Okay, so I've proven very recently, and I've stated a very weak version of this, is that there's some type of chain rule for functor calculus. Okay, so this is recently due to Blon's Blom, and less recently in the case spaces and spectra due to Ron-Ching, and it's asserts that okay, the derivatives have some type of lax monoidal structure, and this is what allows us to say okay, the derivatives of the identity are an operad, and then any functor of this form, the derivatives are going to form a right derivatives of the identity module. Okay, so this is just once you know this monoidality, this is like formal, and you can get stronger statements of this, and I'm sure we'll hear later this week. Okay, so this is the interaction of operads and calculus, is that they naturally show up when you study derivatives. So what does it mean to understand the polynomial geometry of some category C? Well, it means to describe the polynomial functors. So there's a very general classification, which is due to Ron-Ching, which says, okay, I have derivatives, and I can consider that as a functor from functors on C to symmetric sequences, and this functor actually has a right adjoint. And further, the adjunction is comonadic when I restrict to polynomial functors. Okay, so comonads are just some very general type of object which encode a lot of coalgebraic structure. And the statement that it's comonadic is saying that you're encoding all of the structure you need to capture the category. Okay, and so this is completely classifying the geometry of categories. But of course, when you have something that's so general, you usually have something to gain by looking at a specific scenario. Okay, so one of the places that Ron and Ching studied was when I take C to be spaces and I study functors into spectrum. Okay, so you can explicitly compute the value of this comonad on a symmetric sequence, and it takes this kind of relatively intimidating form. Essentially, what's going on here is maps from Lie, all these Lies. Okay, so first off, there's a couple things going on. The first is, why does the Lie operad show up? Something they proved earlier is that the derivative of the identity in spaces is the Lie operad. Okay, and then it basically turns out that this type of structure is very closely related to the structure of a right Lie module. In particular, you kind of expect to get maps which roughly look like this for a right Lie module. But the big difference is that in a right Lie module, you're going to be asking that certain maps are sigma n equivariant, and the way you encode that is you map into fixed points. Okay, but here we have homotopy orbits. And so the kind of assertion is that if I compose with something called the sigma n norm, I would basically have a normal definition of a right module, but any derivatives of a functor spaces to spectra actually is going to factor through the orbits. Okay, so this is commonly called a divided power structure when I have this type of gadget. And so this assertion is that if spaces, their derivatives should basically be a divided power right Lie module. Okay, so a lot of operad stuff going on in a short amount of time. So feel free to slow me down. Okay, but anyways, this is so they've taken the general classification and studied it in a specific case.
What are bounded symmetric sequences?
Bounded, yeah, is a great point. So I restrict to polynomial functors, which in particular means at some stage they stop having more monomials of higher degree contributing. So when I take the derivatives, it's going to be contractible above a certain degree, and that's what bounded means. Okay. Yeah.
Can you say what you mean by like equivalence there?
Yeah. So I mean, here's a category, polynomial functor C to spectra. And then there's a category of coalgebras for a comonad. And the assertion is that there's a canonical map, and that is an equivalence.
Can you say something in terms of algebras instead of coalgebra?
You can in specific cases.
Okay.
I'd be interested to know if there's kind of a general algebra. We'll kind of, we'll maybe we can talk about it later.
Okay.
Yeah. Okay, thanks. Okay, so, I just told you that, okay, derivatives have a right module structure, okay, that's this circle. And then, in the specific case of spaces, they have some divided power structure, at least when O is lead, okay, or in the case of spaces, yeah. And then in general, they form coalgebras over some comonad, okay? So a very just basic thing I could expect, okay, maybe I have some categories where the right module structure completely classifies the polynomial functors. Maybe it happens, okay? And then maybe I have another class of categories where divided powers completely classify it, okay? Because basically I know spaces should fit in there. And then the only theorem so far is that, okay, coalgebras over this comonad, as the comonad varies, definitely classifies it, okay? So let's try to understand if this is accurate or not. Okay. So I'm going to be talking about semi-additivity. And when I say semi-additivity, I always mean one semi-additivity. And the way you define this is in terms of something called the norm map. Okay, the norm map exists for finite groups, and it compares the homotopy orbits to the homotopy fixed points. Okay, we're semi-additive if that's always an equivalence. This should actually not be that scary because the kind of the most common thing we know is that when I work rationally, I always actually do have this equivalence because something, I add everything up and then I divide by the order of the group, which is invertible when I'm rational and I'm finite, okay? So when I work rationally, that's a localization where all of these norms are equivalences. But in general, you're very far from having this be an equivalence if I just work in spectra. Okay? So this is sometimes encoded in this thing called the Tate construction, which is just this cofiber. Okay, so if I wanted to be very egregious about this geometry, I would say something like C is infinitesimally semi-additive if its stabilization is semi-additive, okay? And I do want to be egregious. Okay. So let's do a geometric characterization of this, okay? I expect maybe some people already know this. Is we have these equivalent things, okay? The first is that this stabilization is semi-additive. The second is that it turns out polynomials are classified by right modules. And the third is that, oh, that operad O, well, that's definitely going to be the derivatives of the identity, okay? Something like this is kind of sketched out in a Rowan Ching's original paper. So let's give a quick proof of this. Maybe I should pause to let people digest. So the chain rule is giving you this right module structure on the derivatives from a functor spaces or C to spectra of C. And then we're studying under what scenarios does this completely capture the polynomial functors, okay? And the assertion is that it's when C is infinitesimally semi-additive, okay? When the stabilization of C is semi-additive. Okay, so it's quite easy to prove. Essentially what happens is that Aron and Ching demonstrate that the obstruction for the right modules to be a to capture the polynomial functors is precisely certain Tate constructions. And the Tate constructions live in the stabilization of the category, and we've just assumed that that is semi-additive, and so they vanish, okay? And so this semi-additivity assumption is going to easily imply this classification in terms of right modules, okay? If I have a classification in terms of the derivatives, you know, that this norm map is an equivalence, it turns out basically I can move a result about functor spectra to spectra to spaces. Okay, so if I have a functor spectra to spectra, I precompose with sigma infinity C, and it's going to actually imply that the Goodwillie tower of this thing splits. But this is actually like kind of classically known to imply and be implied by the semi-additivity of this category. Okay, this is work of McCarthy and Kuhn about, it's written for like TN local spectrum. And then finally, this assertion about symmetric monoidality of the derivatives. This is kind of work in progress with Malin, with Niall and Thomas. It is, we basically give models of the derivatives for which this is going to be relatively easy to prove. Finally, we don't talk about the last one because it's not very interesting. And the hardest part is that you remember what these numbers correspond to. So let's just move on, okay? Okay, so the thing you kind of need to start with is defining what a divided power right module is. So I'm going to give some definition. So associated to an operad O, there's this symmetric monoidal category called the envelope of O. This thing, symmetric monoidal functors out of it classify O algebras. That is kind of the classifying property of the category. But if I drop the symmetric monoidality condition, I just get some kind of interesting category of functors, and I call those right comodules. Okay? This is supposed to be formally dual to the definition of right modules, which is when I take pre-sheaves on the envelope. Okay. I've kind of written this subscript here, and it's just because we really have to be talking about, enriched functors if I'm working in a localization of spectra. Okay, but here's something I can define. And if I have my operad reduced, which means that the 0th term is contractible and the first term is S0, or the sphere spectrum localized, then I always have some type of augmentation of it to the unit for operad composition. And right comodules over kind of the unit are just symmetric sequences. And so I get this adjunction, which is, okay, if I have a symmetric sequence, I can give it the trivial right comodule action, and this has an adjoint, which is the indecomposables. Okay. So a fashionable way to define divided powers is simply as a comonad, a coalgebra over the triv indecomposables comonad. Okay, so this is why you expect kind of coalgebras to come up rather than algebras. Okay, the reason it's called divided powers is because very similarly to Aron and Xing's kind of computation of the comonad on spaces of spectra is you just compute it, and it turns out it's going to basically look the same pointwise. In particular, it kind of encodes this lift. Okay, but anyways, this definition kind of exists for any operad, not just for the operad.
Can I ask you that why everything working with SPE again?
I mean, first off, everything's true, but there's going to be some applications to localizations of spaces at the end.
But so far everything is.
Sorry. Why I say SPE is because it has a smash product. The point is I want some smash product on my category to talk about the polynomial functors as a symmetric monoidal category.
Also, the classification of homogeneous layer, the way you state.
Yeah. This is also true. I want to talk about symmetric sequences as well, and have smash products appear in the layers and stuff like this. Okay. So we just defined divided power right modules using some kind of formula. I didn't even mention this, is that Cazul duality kind of implicitly appeared or explicitly appears here. And I mean, somehow this is just a product of defining it this way rather than some more explicit manual way. As far as I know, it's very difficult to define divided powers without using Cazul duality. Cazul duality comes up, maybe I should say this explicitly, is like, why does Lie come up in the Goodwillie of the derivatives of the identity? It's basically because spaces always have a diagonal, which gives them a commutative coalgebra structure, and Lie is the causal dual of Com. Okay, so somehow these kind of appearances of Cazul duality are for the same reason. Okay, so here's something you can prove, very similar to what Greg and Michael prove, is that there's going to be an equivalence of polynomial functors from spaces of spectra using this definition of the right divided power right Lie modules, we get an equivalence there. And then you can explicitly compute the divided power structure. And it takes this form, okay? Essentially what happens is I take my functor, my polynomial f, let's restrict it to finite sets, okay? Finite pointed sets is a kind of closely related to the envelope of the commutative operand. In particular, if I take covariant functors out of it, this is something like co-augmented commutative comodules. And if I take values in a stable category, this is equivalent to non-unital comodules. And then I can just use my theory of indecomposables, trivial things. And when I take the indecomposables of a non-unital commutative comodule, just by definition, that thing is a coalgebra over that comonad from the last slide. Okay. This is this classification is causal dual, and we might hear about it in Greg's talk later this week. It's causal dual to a classification by Dwyer and Resk. So I'd like to maybe mistakenly give a proof of this. So basically the idea is let's prove it for representable functors, and then conextend to get all functors. Okay. So for representable functors, this polynomial approximation, it can be computed in terms of maps of right Lie modules. Okay, so basically I just apply the Onetta lemma, and I take derivatives landing in right modules. We are asking about the restriction to finite sets, so I take a representable associated to a finite set, which is this sigma infinity I-fold Cartesian product. Okay, the derivatives of that is very simple, and it's very closely related to just the homogeneous functors. Okay, recall the homogeneous functors are these I-fold smash powers of sigma infinity together with some coefficient spectrum. But recall that there's this splitting theorem, right? Like the Cartesian product, stably it has a summand of the smash powers, and if I did it many times, I would get many of these things. So in some sense, the Cartesian product derivatives split into a bunch of combinatorics plus the derivatives of the homogeneous functors, okay? The derivatives of the homogeneous functor is basically as trivial as possible. And so when I map out of it, it turns out that I'm computing the right Lie module primitives, okay? Right, why do the primitives come up? When I map out of something with a trivial action, it has to necessarily map into the primitives, okay? Primitives of some action are when the action is trivial, okay? But then all of this extra combinatorics explains why I have this epsilon, okay? Okay, so basically then that's not the statement of the theorem I had. The statement of the theorem had a indecomposable, not a primitive. And so, you know, I just apply these, first I applied the kind of inverse to the augmentation unital thing. But then I need to study Cazul duality for the derivatives of this, okay? And the thing we need to use is that the derivatives of the representables for a finite cell complex satisfy this Tate vanishing, the Tate construction vanishing. And so there's some work of Aron Ching which basically shows that this co-unit is an equivalence. And from this, we're going to deduce the stated result for the representables, okay? The reason it's important to do it for the representables is because this formula is not always true, but it is true for the representables, okay? But then in the statement, everything on both sides commutes with colimits, and so we can conextend. And that gives you it for a general functor. And then the reason it classifies it is this thing about Dwyer-Resk. Also, Lurie proved that the restriction to finite sets classifies polynomial functors, okay? So you throw all of these things together and you get the restriction. Okay. Yeah.
Mentioned that in commits with colleagues you can just can extend, but don't you have to also to check that it's local with respect to the integration of polynomial equations? Or like things like.
Polynomial approximations, when I land in a stable category, kind of commute with colimits. And so like one way to form the polynomial approximation of a general functor is to con-extend the polynomial approximation to the representable. Does that sound right? Does it answer your question?
Yes.
Okay, I mean, I'm not perfect at this stuff, so there's a chance that I messed up somewhere. Okay. Basically, none of that works for a general category. Somehow the most important part is that spaces contain the category of finite pointed sets. Okay, and a general category doesn't contain anything like finite pointed sets. And so how could I try to generalize this? The only thing that generalizes is the observation that the derivatives of representables have vanishing Tate construction. And so we define differentially semi-additive categories to be ones for which the Tate construction vanishes, at least on kind of small objects. So a very stupid example is if C is already has semi-additive stabilization, then set C will be differentially semi-additive because, well, where do the kind of homogeneous layers come from? They come from C, and so the norms will automatically be equivalences, and so the Tate constructions will vanish. Okay, a more interesting example, which was used in the last proof, was that spaces are differentially semi-additive. Okay, they definitely aren't infinitesimally semi-additive because Tate constructions don't vanish in spectrum. Okay, and then a non-example is that actually spectra is not differentially semi-additive because you can compute the derivatives of representables. For instance, so here's why COM shows up in Goodwillie calculus is because if I look at the derivatives of loops infinity, sigma infinity, this is in some sense the representable associated to the sphere spectrum. You have to be a little careful with that, interpret it in the correct way. And the derivatives of that are COM, okay? But COM definitely, the Tate constructions don't vanish for COM. I think I want to say. Yes, these are the extended powers, okay? So those are very interesting. Okay, so we have examples that are trivial, examples that are interesting, and examples that don't work. Okay, so let's kind of try to understand these categories. Okay, so if I have a category that satisfies this Tate vanishing for things associated to the representables, it's going to imply that actually its polynomial functors are classified by divided powers on the right module structures. Okay, of course the operad O is going to be the derivatives of the identity, and the lift is going to be unique. Okay. And then finally, there's some kind of Goodwillie calculus condition that lets you, determine if my category actually has this property. Okay, so I can associate to any functor f this kind of Yoneda type gadget, which is measuring basically how good Pn minus 1 is at approximating the representable functor. Okay, and the thing that needs to be satisfied is that this needs to actually be a polynomial functor, okay? In general, like if I do it for spectra, it turns out it's not polynomial. Okay, so all of these are equivalent. So I won't talk about the proof, but I'll rather kind of get to some applications. Okay, so let's say an operad has significant Tate vanishing if this forgetting the divided powers map is an equivalence. Okay, so that's telling us there's no interesting divided powers. Right modules are the same as divided power right modules. This happens quite a bit. For instance, the EN operad, it has this kind of finite cell complex in an equivariant way description, and this actually implies that the Tate constructor vanished. Okay, so there are no interesting divided powers for the EN operad. Okay, so like essentially this theory of kind of primitives trivial, because dual duality, in this setting was studied by, Michael and Greg in a paper called like manifolds and K-theory. Okay, so it happens a lot. It happens for operads we're interested in. And it's going to turn out that if I have this differential semi-additivity, these are precisely equivalent, okay? The derivatives of the identity kind of don't give interesting divided powers, and the stabilization of C is infinitesimally semi-additive, okay? If you actually think about it for a bit, it's quite strange. This is basically saying there's not going to be a category C where its polynomial functors are classified by right EN modules. Okay, so there's plenty of categories whose derivatives of the identity are EN, but they will never have divided power classifications unless you're kind of working local to a category of spectra which has vanishing tape constructions. Okay, it's something which, I don't know, this is kind of what led me to try to understand this project, was because I precisely wanted to simplify divided powers by working over kind of such an operad, but I realized you can never make it too simple, okay? So anyways. So let's talk about algebra categories. Essentially what I was just talking about is if I have algebras over a spectral operad, the semi-additivity is just determined by where I'm taking algebras, okay? So how do we prove this? Well, our characterization of differential semi-additivity says that if my functor is classified by these divided powers, it's actually has a contractible space of natural divided power structures. Okay, but any right module actually occurs as the derivatives of some functor. Okay, there's this bar construction I can form where I put in an O algebra here. It has a left action of O, and then right R has a right action. So I can form this bar construction. Its derivatives are R, but if I'm differentially semi-additive, it implies that it has divided powers. Okay, so any right module R has divided powers, and it actually has a contractible space. And together that implies this equivalence, which is how we defined significant tape vanishing. Okay, and what that actually means by the previous corollary is that the stabilization, which is just E local spectra, is infinitesimally semi-additive. Or sorry, it just has vanishing tape constructions. Okay.
In the statement, only the left-hand side has got O and the right-hand side has no.
Yes, that's so the operad doesn't matter. Yeah. Okay, so it's basically telling me that algebras behave extremely differently than spaces, because spaces do have a divided power classification. Lie algebras, so here's something which I've kind of implicitly used is Lie algebras are kind of like the algebra version of spaces. Their derivatives of the identity are Lie, okay, but their polynomial functors are very different, is what this assertion is saying. Okay. Right, so for instance, let's take let's take EN. This thing has the same category of right modules and divided power right modules. Because you have tape vanishing, technically the derivatives do have divided powers, but they don't classify the polynomials. Okay, so somehow just having natural divided power structures, if they exist, it's not enough to show that they classify. Okay. Okay, so let's talk about some type of application. Okay, so I want to study localizations of spaces. Okay, so I start with some connected spaces, and I localize at some class of weak equivalences. I'm going to call it snake type if you just supply me with some square. Okay, so this is a square which compares stabilization of spaces and stabilization of the localization, and basically it turns into just a localization of spectrum. Okay, so you give me this square, and then further I get this technical condition which says, okay, if I can find some compact or small enough generators here, which lie in the image of finite complexes, from spaces. Okay, so there's just some technical condition that allows us to do math. And that's what makes it a snake type localization. Okay? Some examples of this are, okay, if I took simply connected spaces and I rationalized them, then the stabilization is going to be rational spectra. And this is what like Quillen and Sullivan studied when they were doing rational homotopy theory. Okay, there's kind of been progress in that front by Bausfield and Hoyts, where they studied something called VH periodic spaces. Okay, this is very complicated category, but essentially I have some class of equivalences called VH equivalences. Okay, I assume my spaces are connected, and then I localize. And then the stabilization is given by something called the telescopic spectrum. Yeah?
I'm confused about the definition. Like, you can look a snake type localization is a localization such that this diagram commits or
Yes. This diagram is, to my knowledge, not something that you automatically get. Maybe you do, but I don't think there's a reason that it commutes automatically. Okay.
SP of E is like spectral.
Yeah, it's just some E-local spectra. Okay, so it's there's kind of a nice counterexample to like I can consider spaces localized at integral homology. This is a useful class of spaces, and it's not true that the stabilization of this category is spectra localized at integral homology.
Yeah, but is it true if you allow the second condition? Or?
Oh, I don't know. But anyways, that example was told to me by Maxime Ramsey, so I should give credit where it's due. Okay, great. So here's some kind of class of localizations. Okay, sometimes something is snake and sometimes it's not. Here's an example where it is. So we have some pretty easy propositions, which is that if I have a snake type localization, the derivatives of the identity are going to be some localization of Lie. And then maybe slightly more interesting is that it's actually still going to be differentially semi-additive. Okay, so this type of localization doesn't affect differential semi-additivity, and it also doesn't affect the derivatives of the identity. Okay, so here's a corollary. If I have kind of an algebraic model, even up to polynomial equivalence, of my localized spaces, as long as I assume that it's a snake type localization, then the algebras will be Lie algebras, and it would be Lie algebras in a semi-additive category. Okay, so what this is saying is that if I try to enforce algebraic models of spaces to exist, I automatically have a kind of a, you know, the take instructions must vanish, and you can even relax this enough to polynomial equivalence. Okay. So if you go, you know, a decade back or however long, there's some work on Matthew Clausen, or there's some work by Matthew Clausen on tape vanishing. And you might expect it could be used to prove a statement like this when I just talked about equivalence of categories. What they study are like basically loops infinity of maybe sigma infinity of classifying spaces. But you have to be a little careful just because things like the VN periodic spaces, they assume the space is connected. Okay, so you have to be a little careful because path components might actually matter. But if you ignore path components, basically, if I have an equivalence from spaces to algebras, there's something called a Bausfield-Kuhn functor, which on the algebra side is just, let me take my algebra and forget the algebra structure and just get a spectrum. Okay, that supplies something called a Bausfield-Kuhn functor, and it implies tape vanishing. Okay, but in particular, you kind of need an equivalent. You need the kind of set of underlying objects to be this. Okay, so here's a kind of a lame picture, which is we altered our picture from before, which initially, you know, was like I have right modules, it has some intersection with divided powers, But we realized in practice, actually, whenever I have a right module classification, the stabilization is semi-additive, and so it actually implies that it's the same as the divided powers. Okay. But I found it quite fruitful to just kind of go back and forth in this picture and try to understand some of the categories we know and love. So I just wanted to end with some questions that I don't know the answers to. What O actually have their divided power right modules classify polynomials? Basically, the only thing we know is that some localizations of the Lie operad class their right modules divided powers classify polynomial functors from spaces to spectra. Okay, so Lie is the only thing we know that fits into here. And then more generally, what if I just gave you a comonad on symmetric sequences? When do its coalgebras give polynomial functors? Okay, the kind of general class of examples was given by Ronan Ching, but maybe somehow you can write down a condition. And then finally, there's other notions of kind of equivalence of categories, which are weaker than just actual equivalence. One thing I could do is I could use Heiss-Hoytz's Goodwillie approximations of categories. Okay, what Heiss does is he says, let me study the Goodwillie tower of the identity in the infinity category of infinity categories. And so something I could say is, okay, what if I have C and D and I give you an equivalence from P infinity of the identity of C to P infinity of the identity of D? Is that the same as polynomial equivalence? Is it more strict? Is it less strict? I don't know. But it seems like a natural question to ask. And that's all the questions I have to ask. So thank you.
So you can like usually when you have categories you can talk about monetary equivalence of two categories and like the minimal envelope of Morita like thing is like the independent completion. Do you know if there is maybe something similar to idempotent completion but for polynomial?
Yeah. I feel like if I kind of knew the definition of idempotent a little better, I'd have a better answer. I mean, this is definitely a type of Morita equivalence. So I kind of expect the answer is what you expect, but I feel like I can't say it off the top of my head. Yeah. Sorry.
Just a bit serious question. On an early slide, you used the derivatives of functors of having a symmetric monoidal structure. Did you mean the word symmetric?
Yes, because this is I maybe didn't make it clear what type of thing I.
Yeah, sorry about that. This is why.
No, it's so this is what 3 implies 2. So the assertion that I'll make is that there's a model of derivatives for which it's symmetric monoidal with respect to pointwise smash product and day convolution of right module.
I see. Yeah.
Yeah, it's not
Not quite.
complicated. That would be horrible.
Yeah.
Yeah.
Thank you.
Those are all the questions we have for
Thank
you too. So we next have a reception right outside the door. I believe Dave also wanted me to reassure everybody that we will not run out of coffee in the morning. He's ensured that won't happen again. Is there anything else? Somebody in the room? Okay, well, let's thank Connor again.